Hi everyone, welcome to the fourth lecture of the series on control of power electronic converters. In this lecture, we discuss the analysis of DC to DC converters. Here is the overview. We start with the basic ideas about the solution of the state equations and the state trajectory of DC to DC converters. Then we discuss about the equilibrium point and steady state operating points for the converters. And finally, we discuss about the stability analysis of converters, in which we focus on the Lyapunov approach for stability. Let's start with the second order differential equation as given in equation number 1. By defining the state variables x1 equal to x and x2 equal to x dot, the differential equation can be rewritten as in equation number 2. Here, the second equation is obtained by taking these two terms to the right hand side, which gives x double dot equal to minus 2x minus 3x dot. Now, by defining the state vector x and the system matrix A as given in equation number 4, we can represent the state equation as in equation number 3. And from the linear system theory, the solution of x dot equal to ax is obtained as x of t equal to e raised to at x0, where e raised to at is an n by n square matrix which transforms the initial state to the current state, and x0 is the initial state. In this example, e raised to at will be a 2 by 2 matrix, and it consists of the terms e raised to lambda 1 t and e raised to lambda 2 t, where lambda 1 and lambda 2 are the eigenvalues of the matrix A. Now, for the second order example, we can have the response as in figure 1 for an initial state x0 equal to 10 and 0. Here, the first subplot shows the plot of x1 versus time, and the second one shows the plot of x2 versus time. And the last subplot is the state trajectory of the system, in which we plot x1 versus x2. Similarly, figure 2 shows the plots of the states and the state trajectory for different initial conditions. Here, the initial conditions are chosen as 10, 0, 0, 10, minus 10, 0, and 0, minus 10. And for all these initial states, the states are converging to origin, which can be observed from the figure. We call the plot of the state trajectory with the different initial conditions as a phase portrait. So here, the last subplot will be a phase portrait for the second order example. Now, based on the eigenvalues of the system matrix A, we can have different classes of phase portraits, which are node, saddle, focus, center, etc. If the eigenvalues of A are real with same sign, we call the phase portrait as a node, and it will be as shown in figure 3a. And if the eigenvalues are real with opposite sign, it is called as a saddle, which will be as shown in figure 3b. Similarly, if the eigenvalues are complex, it is called as a focus, for which the phase portrait will be as in figure 3c. And finally, if the eigenvalues are imaginary, the phase portrait is called as a center, and it will be as shown in figure 3d. In the second order example, we had the eigenvalues of A were both real and negative. Therefore, the phase portrait comes under the class of node. Next, we move on to the solution of the state equation for the buck converter. Let's recall the switched system model of the buck converter from previous lectures, which is of the form of equation 6, and the subsystems will be as in equation number 7. And we have the solution of the state equation for the subsystems can be obtained as in equation number 8. Here for subsystem 2, we have B2 is equal to 0. So the solution will be similar as in the second order example. Whereas for subsystem 1, we have B1 is not equal to 0. Hence, the solution will be x of t equal to e raised to a1t x0 plus xp, where xp of t is the particular solution due to the affine time b1. Now, for the buck converter with parameters as given in equation number 9, we have the state trajectory for subsystem 1 as in figure 4. Here, we can see that the states x1 is converging to the value 10, which is same as V in, and the state x2 is converging to 5, which is equal to V in by R. Therefore, the state trajectory will start from 0, 0 and goes to 10, 5, which is the steady state value of x1 and x2. Similarly, for the subsystem 2 of buck converter, we can have the response as in figure 5, where the state trajectory starts from the initial state, which is set as 10 and 5, and it converges to origin. Here, the state trajectory for subsystem 2 is equivalent to the second order example that we considered initially. Now, in the buck converter, either subsystem 1 or subsystem 2 is active at each time instant based on the switch position. Therefore, the state trajectory will either move towards 10, 5 or 0, 0. Now, using state trajectories for subsystem 1 and subsystem 2, we can construct state trajectories for any arbitrary switching signal. Here, one important observation is that if we are switching to subsystem 1, the capacitor voltage will be increasing to Vin, and for subsystem 2, the capacitor voltage will be decreasing and it decreases towards 0. Therefore, if you want to increase the output voltage, we can switch to subsystem 1 and otherwise to subsystem 2. This gives us a simple switching scheme for buck converter in which if the current output voltage is lesser than the desired voltage, we switch to subsystem 1, otherwise to subsystem 2. This situation is illustrated in equation number 11, in which we consider the desired output voltage as 5. And if x1 is lesser than 5, we set sigma equal to 1. In other words, we switch to subsystem 1. And if x1 is greater than or equal to 5, we set sigma equal to 2. The states and switching signal for this switching scheme is given in figure 6, which also shows the plots of the state trajectory in green color. Here we can see that once x1 is reaches 5, we will be switching between subsystem 1 and 2 in order to maintain x1 at 5, which results in the steady state oscillations in x1 and x2, which we also call as the ripples. Next, we briefly discuss about the equilibrium point and steady state operating points of DC to DC converters. We have at the equilibrium point x equal to xeq, the derivative of the state vector x dot equal to 0. In other words, once we reach the equilibrium point, we will be staying there since x dot is 0 at the equilibrium point. Now, substituting this condition for subsystem 1, we get a1 xeq1 plus b1 equal to 0, which gives xeq1 is equal to minus a1 inverse b1, which will be equal to Vin and Vin by R. Therefore, the equilibrium points of subsystem 1 will be Vin and Vin by R, which gives the steady state values of the states x1 and x2 if we are using subsystem 1. Similarly, for subsystem 2, the equilibrium condition gives xeq2 equal to minus a2 inverse b2, which will be 0, 0, since b2 is 0 for subsystem 2. This means that if we are switching to subsystem 1, the states will converge to the values Vin and Vin by R. Similarly, for subsystem 2, the states will converge to 0 and 0, which we also observed from the previous simulation. Next, we discuss about the steady state operating point of DC to DC converters, which we can also call as the desired equilibrium point. In the case of converters, the desired equilibrium point will be different from the equilibrium points of individual subsystems. Therefore, we have to switch between the subsystems in such a way that the states of the converters are converging towards the desired equilibrium point. And also, the states will stay at the equilibrium point or at least stay in a bounded region around the equilibrium point in steady state. In order to discuss about the steady state operating point, we consider the averaged model of the DC to DC converter, which will be as given in equation number 13. For the buck converter, we have A1, A2, B1 and B2 as given in equation number 14. And we denote the steady state operating point as xeq, which is basically the desired equilibrium point of the converter. And we have x dot should be 0 at x equal to xeq. Now for the state space averaged model given in equation number 13, if we substitute the steady state condition x dot equal to 0, we obtain equation number 50, in which we can substitute for A1, A2, B1 and B2 for the buck converter, and this gives xeq as d into xeq1 plus 1 minus d into xeq2, where d is the duty ratio of the converter, which takes a value between 0 and 1. We have d into xeq1 plus 1 minus d into xeq2 will be a converse combination of xeq1 and xeq2. This implies that for the buck converter, all the points in the line segment connecting xeq1 and xeq2 can be considered as steady state operating points. We have xeq2 is equal to 0 for buck converter. So this final expression is basically equal to d into xeq1. Here we can also observe that for the buck converter, the steady state output voltage, which is equal to the steady state value of x1, equals d times Vin, which is basically the defining relation for the buck converter. And by varying the duty ratio d between 0 and 1, we can obtain any voltage between 0 and Vin as the output voltage of the converter. Figure 7 shows the steady state operating points for the buck converter, which is basically a line segment connecting xeq1 and xeq2. Here xeq1 equals Vin by R and xeq2 equals 0, 0. We can operate the converter at any point in this line segment by switching the converter with the corresponding steady-state duty ratio. The operating point is decided by the load requirement, which will be in terms of the voltage or current. Similarly, for the full bridge converter, we have the steady-state operating points will be on the line segment connecting XEQ1 and XEQ2, where XEQ1 equals Vin by R, and XEQ2 equals minus Vin by R. We have for buck converter and full bridge converter, the system metrics was same for both subsystems. That's why we obtained the steady-state operating points as a line segment connecting XEQ1 and XEQ2. For other converters such as boost converter, buck boost converter, etc., we have A1 and A2 are not the same. Therefore, we can have the general equation for the steady-state operating points as in equation number 16, which gives XEQ2 equals minus AD inverse BD, where AD and BD are functions of the duty ratio D. And for each duty ratio D, we get a different operating point XEQ2. Next, we move on to the stability analysis of converters. Stability can be considered as the ability of the system to converge towards the desired equilibrium point. From any given initial state, we require the system to converge towards the desired equilibrium point. Now, if the system is stable at the desired equilibrium point for a given initial condition, then the state trajectory will converge towards the equilibrium point, or at least it will stay in a bounded region near the equilibrium point. There exist different definitions and approaches for stability. In this lecture series, we will be using the Lyapunov approach, which is mostly used for stability analysis of state space models. Now, as per the Lyapunov theorem, the dynamical system x dot equal to f of x is stable if there exists a positive definite function v of x such that its derivative v dot x is negative definite. We consider the equilibrium point as origin, and in general, any non-zero equilibrium point can be shifted to origin by using a coordinate transformation. Here, the first condition implies that the value of the Lyapunov function at origin should be 0, and for all other points, it should be greater than 0. This means that the Lyapunov function takes the lowest value or minimum when the state is at the origin or the equilibrium point. Now, if the initial state is not at the equilibrium point, we have some non-zero value for the Lyapunov function initially. Then, the second condition ensures that the value of the Lyapunov function does not increases from its initial value. This ensures that the Lyapunov function remains bounded, which also ensures the state trajectory remains in a bounded region around the origin. Now, if we can have a more stronger condition here, like v dot of x is strictly less than 0, then we can ensure that the value of the Lyapunov function decreases along the state trajectory. In that case, the Lyapunov function will eventually decrease to its minimum value, that is 0, which means the corresponding state trajectory will converge to origin. This condition is called as asymptotically stable, which is a stronger condition than Lyapunov stable. By modifying the upper bound for v dot of x in a more stronger or less stronger way, we can have different notions of stability, which will be discussed next. Here, by modifying the upper bound for v dot of x, we can have different notions of stability, which are the practical stability, for which v dot of x is upper bounded by minus alpha of mod x plus m, where m is a finite positive constant and alpha is a positive definite function or KL function. So minus alpha will be always negative. And the second one is Lyapunov stable, for which v dot of x is less than or equal to 0. And then there is asymptotically stable, for which v dot of x is strictly less than 0. Then we have exponentially stable, for which v dot of x is less than or equal to minus m times v raised to c, where m and c are finite positive constants. Similarly, we have quadratically stable, for which v dot of x is upper bounded by minus x transpose qx, where q is a positive definite function. And finally, we have finite time stable, for which v dot of x is less than or equal to minus m. Now, figure 9 shows the plots of the bounds for the Lyapunov function for these different stability notions. For finite time stable, the plot of the Lyapunov function will be bounded by this red curve. So we can see that the Lyapunov function will converge to 0 in finite time. And for exponentially stable, the plot will be bounded by the green curve, which indicates that the Lyapunov function will converge to 0 at an exponential rate. And for Lyapunov stable and practically stable, the Lyapunov function will be space bounded, which basically indicates that the state trajectory will remain in a bounded region around the equilibrium point. The most commonly used Lyapunov function is of the form of a quadratic function, which can be represented as p of x equal to x transpose px, where p is some positive definite matrix which is to be determined. Now for this Lyapunov function, we have v dot of x equal to x dot transpose px plus x transpose px dot. Here we can substitute for x dot from the state equation, and this gives v dot of x for the situation system model as in equation number 19. Similarly, v dot of x for the state space averaged model will be as in equation number 20. And finally, v dot of x for the linearized model will be as in equation number 21, where we have to use delta x as the state vector. Now, in the design of the converter, we have to select the switching signal sigma or the duty ratio d in such a way that v dot of x is negative, or in other words, the Lyapunov function is decreasing in nature, which basically ensures stability of the converter. In the next lecture, we will discuss about the analysis of rectifiers and inverters. That completes this lecture. Thanks for listening.